Okay, hey, Precalc 12B. We are going to talk about analyzing rational functions today. So, this is basically just getting a little deeper into the idea of what rational functions look like, and specifically what some of the behaviors are when you look at the pieces of a rational function. What part of the graph or what part of the function is being affected by certain pieces. All right, so it's 9.2 in the textbook. So here we go. If we define a rational function as generally just being any rational function, r of x is equal to some polynomial function p of x divided by another polynomial function q of x, then we get something that looks like what I have up top. So r of x is equal to p of x over q of x. And we can break these down into a few different types, I guess, or general categories. So what I have listed below is that the three categories that we're going to pay attention to are when the order of the polynomial that is upstairs is the greatest, or is greater than the order of the polynomial q. We're going to take a look at how to tell what's going on when the two polynomials have the exact same order. And we're going to also take a look at what happens when the polynomial in the denominator has the higher order of the two. So when I say order, I mean power. It's the order of a polynomial, if you remember from Precalc A, is the highest power that is present in the polynomial. Doesn't matter whether it's written in ascending or descending order. That's irrelevant. The only thing that matters is when you say something has an order of 4, that means that the highest term or the highest power term present in the entire polynomial is a 4. So here we go. This is an example that we're looking at where the order of p is higher than the order of q. So the numerator's order is higher than the denominator's. I wouldn't really, I call them p and q and r, but really you want to think about it as top bottom, numerator denominator, because it may be that you're working with things where you're not naming them p and q, or they're named something else anyway. So just as kind of a thing to look at, just don't get thrown off too much by that. All right, so for this particular one, our r of x is equal to x cubed minus 2x squared plus 1 over 3x minus 2. So what I'm actually going to do is I'm going to look at the end behavior of these three different categories, because the end behavior are where these categories actually differ the most. They may have and can have similar vertical asymptotes, similar points of discontinuity, similar intercepts, but one of the things that will not be the same for these three different categories that we looked at are going to be the end behavior, otherwise known as the horizontal asymptotes. So let's take a look at the end behavior out to the right hand side of r of x in this case, which is the same thing as just saying the limit as x approaches infinity of the actual polynomial thing there. Actually don't need that bracket, that's okay. And so if we did this the long way, which is okay, what we would do is we would take the highest power of x, and I would multiply the entire numerator by 1 over that power, and I would multiply the entire denominator by 1 over that power. Super cloudy out my window. I'm hoping that's what's making me feel like I need to have a big long sleep in the middle of the day. So let's go 1 over x cubed, 1 over x cubed. This is going to be the first and last time that I do this for these particular types of examples, at least for today, because We have done it before, but it is a little longer and tedious, and I want to get to actually talking about analyzing rational functions rather than spending the whole time with the kind of minutia of the limit treatments. So we're going to go down and say, okay, well, the x cubed would multiply in. That means my first one would just be 1, and then minus 2 over x plus 1 over x cubed. And then in the denominator, we would have 3 over x squared minus 2 over x cubed. Now, the important thing about this is some people actually, well, I noticed on some people's assessments, they were dividing by the, not the highest power of x, but dividing by the lowest highest order, which is a neat way to go about doing it too. So I'm so sorry. So the idea is that you would not end up with these things that approach 0 in the denominator specifically. So that's that would be maybe a little bit safer there, but it's really not that big of a deal. I'm going to do it this way, and this is kind of the way that I'm used to. In this particular case, we would get the limit as x approaches infinity of, and then actually I'm going to apply the limit. I'm not going to write it as separate little pieces. So the limit as x approaches infinity of 1, that's going to just leave us with a 1. The limit as x approaches infinity of this thing is 2 divided by a really big number, approaches 0. This is 2 divided by a really big number cubed, that approaches 0. This approaches 0, and this approaches 0. So overall, we're going to get basically 1 minus 0 plus 0 over 0 minus, I guess, 0, which is 1 over infinity. Now, there are a few different kind of things that look like this that we have been interpreting, but I'm going to go over again just really briefly because I've seen a few mistakes in assignments and things, and it's not just like a few people, it's a good chunk. So there's a difference between this, and this. Very, very, very large difference. This is indeterminate, which basically means we don't know what it is. Usually you can use algebraic means or maybe something called L'Hopital's rule a little bit later on if you take some calculus in order to determine what that limit is going to become. So it could actually be that 0 over 0 does give you something that's undefined. It could be that it's 0, and it could be that it's pi. I say pi, it could be any constant value. So it's not safe without knowing how to deal with it to say that it's any one of those. So for us, when we were doing this, we usually did like factoring or multiplying by a conjugate or maybe putting something on a common denominator and then looking for a factor that canceled afterwards. So if you see 0 over 0, then we don't really know what the answer is. This is undefined. Now, specifically, it may be that the thing is undefined, but when you are coming in from the left and the right, it may be that you have positive infinity or negative infinity. I'm going to check my, maybe I need to open the window and get some more oxygen in here. So the negative infinity from one side, positive infinity from the other side. Say that the limit does not exist. If it's positive infinity from both sides, you could say positive infinity and that would be okay. But it is not a defined real number value, so undefined. This one, it's real fancy. It's 0. So any number 0 or any 0 divided by a real number is going to be 0. So in this particular case, we actually have an undefined situation. So the undefined situation can come from this thing either approaching a positive infinity or this thing approaching negative infinity. Now, probably the easiest way to determine whether it's going to be positive or negative infinity that this thing is approaching is to look back at the original statement and say, which term here matters the most? Well, it's this term. If you take positive infinity and plug it into in the numerator, it's this term. So these two terms are going to be really small when you approach infinity in comparison. So this fellow right here is going to be positive infinity times positive infinity times positive infinity. It's going to be a positive number. Down here, we're going to get just positive infinity times positive 3, so that's going to be a positive number as well. Positive divided by a positive is a positive. So if we wanted to get a little more detail, instead of just saying that that's undefined, we could say that that is approaching positive infinity. And so that will tell us, if we were to graph it, that as we go out to the right-hand side, you're going to end up shooting upwards towards positive infinity. So it's that's what we can get out of the limit comparison. However, we took a long time to talk about that and write down some stuff. So let's make it simpler. If p of x, maybe I'll say if the order, so if order p of x is greater than order q of x, so if the order is higher in the numerator than the denominator, you'll get either plus or minus infinity for the limit as x approaches infinity, or the limit as x approaches negative infinity of r of x. So basically, the rational function every time, if you have a higher power in the numerator, is going to approach positive infinity or negative infinity, and it's going to depend on the signs that are involved here. For instance, if this was a cube over a square and you're putting negative infinity into it, then the cube, the negative infinity, would kick a negative back out. The square, it would become positive, so you get negative divided by a positive, which means you'd approach negative infinity. So it doesn't always approach positive infinity, and it can be a different thing on either side. So it could be that you have this rational function that's doing some funky stuff in the middle, blah, blah, blah. That's one where the horizontal asymptote is 0. I don't know how I did that. So if you had one like this, where you on one side are approaching negative infinity and the other side you're approaching positive infinity, that's okay, and it will happen. So just remember to test both those things if you're looking for end behavior. So general rule is what I have written down on the pad right now, is if the numerator's order is higher, then you get end behavior of positive or negative infinity. All right. Thing 2, if orders are the same, so this is if the order of p of x and the order of q of x are equal to each other, I'm going to do the quick, not much write down method for this one. So we have seen that if this is true and you are looking for the limit as x approaches infinity of r of x, which in this case is the limit as x approaches infinity of x cubed minus 2x squared plus 1 over 2x cubed minus 2x. So you look at the ratio of the coefficients. That's all you do. Because all the time, every single time, all of the lower order or lower power terms are going to become irrelevant as you approach infinitely large values. So they're gone. The only thing that's left is something basically divided by itself with some coefficients involved. If we pay attention to just the divide or the power part, that can cancel out. It's something divided by itself, not close to something divided by close to something. Like it's going to, they're not going to be similar. They're going to be identical because it's the exact same variable to the exact same power. So in this particular case, we would end up with the ratio of the coefficients, which this one, since there's none written in, is a 1, and this one is written in as a 2, so it becomes 1/2. That's going to be what we do if we want to know this limit. So what that means is that there is a horizontal asymptote at y is equal to 1/2. So that's really nice that we can just look at that ratio of the coefficients and use that to determine what the horizontal asymptote is just really quickly. So case 2 is really nice, and it does result in a horizontal asymptote. Actually, I probably can graph, just as we go through, the first 2 examples. Let me go back here for a second, and I think this is the one I want. So x cubed minus 2x squared plus 1 bracket over 3x minus 2. All right, so what we see here is let me projector mode there is a little easier to see maybe. That's what we were looking at. Now, that's a really cool function, but what did we found out about it? Well, the only thing that we had really found out about it, if I kind of reel us back to here, was that as we go out towards positive infinity, this thing goes towards positive infinity, which is what this part of the graph is doing. So if I pull back, we kind of keep exploring up that way. It's just shooting up into the higher and higher y values. That looks fine. If we had done the negative infinity instead, when we were looking at the original function, so that original function, if I put in a negative cubed divided by 3 times a negative, again, just paying attention to the highest powers there, then we would end up with a negative divided by a negative, which is a positive. And so the limit out the other way would also give us this positive infinity. So it goes up and up and up and up. All right, well, that's good. So that's the information that we got out of analyzing end behavior for that one. This one is a little different. So we have x cubed minus 2x squared plus 1 bracket. So I can go into the denominator of that whole thing. All right, there we go. And so this is what we're looking at instead. And you'll notice that as we go this way and this way, we are not approaching the axis. This one passes through the axis actually, and then it kind of just levels off on this side. Now, we stated that the answer to this one, in terms of its end behavior, when we go out to the right was the only one we technically checked, although if we were to go out to the left instead, so if we changed this so that the only thing that was different was it was approaching negative infinity, then these would still cancel out and you'd still be left with just 1 divided by 2. There would be nothing that would be able to change our answer in this case. So if I pull out here for just a second and I kind of comb along at this value, you'll see that it's 0.478 right there. And I'm going to, just for, we'll go up to 1,000 for a moment and just see how those values are behaving there. 0.499. So we said that it should be approaching 0.5. The graph looks like it's really agreeing with that. So I have not seen a place as of this point where the function actually looks like it is above 0.5. So if I come in here for a moment and just 0.5. Now, the thing is that Desmos, depending on your zoom, I guess you could say, is going to give you 0.5 as being what it rounds to. Now, it's going to think out there that it's actually equal to 0.5. it's not. It's not giving you quite enough precision to do that properly. So that's just one of the limitations of things that are being done graphically, is that at some point it runs out of decimal places to work with, and it's going to tell you that 0.4999999999999 is 0.5, and that's okay. So anyway, that looks good out that way, and it would look good the other way too. So as I said, if we put in the limit as you approach negative infinity and you go this way, it would be getting closer and closer to 0.5. So that is our general, I guess, rule then, kind of like we had up here. If order of p of x is equal to order q of x, then the horizontal asymptote is at y equals ratio of coefficients. Now, coefficients of the highest order term. If I was trying to remind somebody to do this, I would just say ratio of coefficients, and I say that a lot. But it's not just ratio of any coefficients, it's the ratio of the highest coefficients. So that's the rule if you have same order top and bottom. Now, if we are to go to another example here, there's only one case left. So you either have highest up top, they're both equal, or of course highest down bottom in the denominator. So the order of Q is higher than the order of P. All right, so I'm going to do the same thing, and I'm going to use positive infinity again. Not really that it matters, but if I'm going to evaluate the end behavior out to the right first, it would be the limit as x approaches infinity of those things over these things. So as you can tell, I probably didn't mix these up a whole lot in terms of the actual terms that are there, but I did mix them up enough so that the order this time here is definitely higher in the denominator. So again, if I were to take everything here and I were to divide it by the highest power of x, which would be the cube, it would look kind of like this. Oh, except for I just noticed that I have a double square up top, which is a little bit awkward. I'm going to take my second term. I mean, we could combine them and it wouldn't be wrong, but it's a little bit sloppy. Here, I'll open up math type for you, and I'll put this in and show you what I'm doing. All right, so r of x is equal to fraction x squared minus 2x plus 1 over 2x cubed minus 2x. We'll do that. I think, of course, when I originally did this one, it was a different settings and math type, so I get a different font. That's okay. All right, so a little bit better. I'm gonna not have that double square there, so it looks a little awkward. Okay, so we have 1 over x minus 2 over x squared now, plus 1 over x cubed over, and then in the denominator 2 minus 2 over x squared. Now, each of the three terms in the numerator is now constant over top of some power of x, which is a number that's getting very large. So that's going to be 0 minus 0 plus 0 over 2 minus 0. Now, we said earlier that any 0 divided by any real number is always 0. So this gives us a 0. Now, because it's 0, the only thing that could change by testing out towards negative infinity is that you would get positive 0 versus negative 0. And that's kind of irrelevant. I mean, it's not if you were doing kind of a nastier function where you have a horizontal asymptote is 0 and it passes above it, bumps up, and then cuts back down versus just stays on the same side. No, the negative 0 would actually tell you that it's approaching 0 from the bottom, and the positive 0 would tell you it's approaching 0 from the top. But what would probably happen is that you would have some math that would let you know that there's a bump there. I don't actually like doing a whole lot of those types of examples before you have calculus, because it really just relies on you using test values for the most part. And it's okay, but I'm just going to say that it gives you a horizontal asymptote of 0, and I don't care getting really into which side it's approaching from. So the end thing there was if the order of p of x is less than the order of q of x, then what ends up happening is that r of x has a horizontal asymptote at y is equal to 0. So 3 cases. Higher order up top, positive or negative infinity is what it approaches out towards the ends. Same order, top and bottom, then it's some ratio of those coefficients. So we got a half, but it could be any value. So you'd look at that ratio, and that is your horizontal asymptote. Again, you may have to test towards positive and negative infinity, although most of the time we're going to see they end up being the same thing. And then, lastly, if the order is greater in the denominator, then it approaches 0. All right. So that was all about end behavior and horizontal asymptotes. Now I'm going to talk about middle behavior, if you wish. So things that are interesting that happen in the middle of rational function graphs. Oh, I didn't even graph last one, which I'll do right now. And then I will go ahead and do this next little piece. Just a second, I'm trying to find... Yeah, trying to find the function that I ended up using. Here we go. All right, so this is x squared minus 2x plus 1 bracket divided by 2x cubed minus 2x. All right, so I'm going to just go back here for a second. So we have this one, and then it is approaching pretty close to 0 on both sides, so that's 0.056, and on this side, about negative 0.07. And again, approaching 0 both sides, great. We wouldn't have found any x-intercepts if we were looking for it, so we know it doesn't like tuck above there, so it's approaching from the bottom. This one does have an x-intercept, so it will go through it, and then it's approaching from the top. That's great. I guess the example where I was talking about not knowing if it cuts back down, you can, that's mostly if you have a horizontal asymptote that's non-zero. Technically, you can just solve for when it crosses that horizontal asymptote and figure out where that happens and know what side of the thing you're on. So you don't have to do it through test points, like I said. So this is one of them, and this is another one, and this is another one. Actually, they all look kind of different. They have their own little unique little twists or turns to them, even though they looked very similar from an equation point of view. So all we've been able to tell so far is how to look at the ends and determine what's happening out that way. So now we're going to come back and talk about what is happening in the middle. So vertical asymptotes versus points of discontinuity. So a vertical asymptote occurs in the middle of your graph when you get some sort of infinite behavior. So we've seen that infinite behavior tends to come from things being divided by 0. And it might be a positive 0 or a negative 0, depending on what side you're approaching from. But it's when you take some value and you divide it by 0 that you end up having this kind of infinite behavior. Now, when does that happen? Well, it can happen, for instance, if we have x plus 3 divided by x minus 1. It's a very simple rational function, linear over linear. And so as we approach an x value of 1, then this function starts getting wonky. So upstairs, it's going to be 4, which is fine. But downstairs, it's going to be, and I probably should, I'm just, not that it matters because it would have been anything when I was talking out loud. But the thing that I have is going to be 4 over 0. So we would have 4 divided by 0. And so it's going to have this behavior that starts to go, shoots way up or shoots way down. But that's not out towards the ends anymore. That's at an x value of 1. So we're almost smack in the middle of things here. And so it has this infinite behavior going on. That's what a vertical asymptote is going to come about because of. Infinite behavior in the middle of your graph. Okay. So we'd have a vertical asymptote here of x is equal to 1. Point of discontinuity, POD for short, is interesting because a point of discontinuity this is actually a really funny graph, but those occur if you basically get that same sort of behavior at the same time in both the numerator and the denominator. So if, I don't know, if we approach. So over here, if we approach x of -3 in this particular case, then we would get towards this 0 divided by 0. But as it gets extremely small, as it approaches 0 in the numerator, it's exactly the same thing that it's approaching in the denominator. So if you take something that's unspeakably small divided by something that's identically unspeakably small, we still have something divided by itself, which gives you 1. So in this particular case, this would actually give you a value of 1 no matter how close you get. However, when we're talking about that, we're talking about limits. There is no real number that describes exactly 0 divided by exactly 0. We just don't have, if you want to see that, if you had x is equal to 0 over 0, you wanted to solve for x, well, it would be 0 times x is equal to 0, and then, well, what does x have to be in order for that to be true? I guess anything, but that's means that we don't have a value for it, and it's kind of weird. So don't get too bent out of shape in trying to think about at the actual point what's going on. Actually, this is kind of a funny function because it's something divided by itself, which at pretty much every other value, like if we put in an x value of 1 here, then it would be 4 divided by 4, which gives you 1. What if we put in an x value of 2? Well, it'll be 5 divided by 5, which gives you 1. And so this is like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, except for all the values in there would be 1s too. Except for there's a very special point at x of -3 where this thing does not exist. Sometimes people will call it a hole, and other times we'll just refer to that as the point of discontinuity. So we will use an open circle in order to represent that. So even if the open circle exists for values that are bigger than, well, I don't know what I'm trying to say. So even if the open circle takes up more space than the idea that it only is a very singular point, that's okay. You can't really avoid that. And if you want somebody to see it visually that there is a hole there, then you pretty much need to draw it larger. Now, you can definitely also have. I should change this over to a partial erase and kind of do the middle. A lot of times you'll have the hole like be apparent because you actually have nothing in the middle. So I was just drawing it over top of my graph there. It's a lot more clear if you don't, but it's not too big of a deal either way. All right, so that is kind of the behavior of vertical asymptotes versus point discontinuity. So putting them side by side, vertical asymptotes, you get the behavior that you're approaching positive or negative infinity at some interesting point somewhere in the middle. Point of discontinuities, you're getting that same sort of behavior, but it happens identically in the numerator and denominator at the exact same time. And so it basically cancels out, but you still are not allowed to have a point there. So it basically seems like nothing's going on. But at that point, it's not valid. So I'm going to just kind of put these two things into Desmos for a second and let you see the difference there. So let's go, I've got a graph. And so this is x minus 3 over, oops, I didn't put my bracket, over x minus 1, except for that's plus 3. Not that it really matters, but x plus 3 divided by x plus 3. All right, so this one here is kind of like your typical rational function. It's got these nice little tutus things. And if we were to look at this vertical asymptote that occurs, we said that it happened at 1. That looks really good. So it basically splits right down. And as we said, when you divide by a number that gets really close to positive 1, like 0.99999, then all of a sudden this thing just kind of shoots up there. I'm not even at near value instead of 0.9. So this is like 0.779, and it's already at negative 17, and it's just going to get crazier as we go down there. So, 0.936, we're already up to negative 61.5. On the other side, it's going to shoot up the positive direction, but same idea. And the split in the middle happens at 1. And so there would be no value that's allowed to happen at 1. It is not a part of the domain. So that's a big thing to notice there. All right, next up, I'm going to take a look at this one. This graph is not deceiving you. It is a horizontal line at y is equal to 1. So it just is 1 everywhere. Now, Desmos is pretty good about this. So if I go in to negative 3 and I say, well, it's 1 everywhere, but we said it doesn't exist at negative 3. Oh, look at that. Good job, Desmos. So it knows that there is not supposed to be a value there. So it doesn't like to represent it as a big open hole all the time, which is, I don't know. It's because all of these points, no matter how close you are into it, they all exist. So Desmos is drawing this by using probably, I'm not making a bit of an assumption here, but it's using a bunch of points all plotted together to make it look like it has this just kind of like line curve type shape to it. But because of that behavior, it is a little bit weird. I suppose they could just make the undefined spot and then like superimpose it on top and have it cover what was underneath. But that's a little bit weird too. So anyway, that's what's going on in the case of a vertical asymptote or a point of discontinuity. Now, so these basically occur because of a solution in your denominator, vertical asymptote, a factor in your denominator being equal to 0. So factors, vertical asymptote. Factors up top are actually x-intercepts. So the only time when the whole thing has a value of 0 or y value of 0 is if you have something in the numerator that causes it to be 0 divided by some value. If you have same factor in both, then it's a point of discontinuity. So what we will probably do when we're analyzing these rational functions is we will say, let's take a look at the x-intercepts. So you do where are the factors in the numerator equal to 0. You'll take a look at the vertical asymptotes. And then you will cross some of your answers out if you find that they're in both. So if you find that you have an x-intercept at x is equal to 1 and you have a vertical asymptote at x is equal to 1, that can't be true. And it's not true. It's the special case of a point of discontinuity. So you would have a point of discontinuity occurring there instead of either of the vertical asymptote or x-intercepts. So as kind of a demo, let's see if I actually have one here. No. So if I were to have a really nicely already factored version of a rational function. So if I have this, okay, so 3 factors over 3 factors. We can tell a lot of information really quickly about this one. So thing number 1, highest order is 3 in the numerator, highest order is 3 in the denominator. The ratio is going to be 1 over 1 because it's just x times x times x, x times x times x. So this has a horizontal asymptote at y is equal to 1. We can get that out of the way right away. It has vertical asymptotes at x is equal to. Now, technically it's every single piece in the denominator is what we look for. However, if there's a piece in the denominator that is also shared with a piece in the numerator, then that will not be true at that particular point. That one's the only one that shares, so we can say the other two are going to be x is equal to -1 and x is equal to +4. Vertical asymptotes. We have a point of discontinuity at x is equal to -2, and we have x-intercepts at x is equal to 1 and x is equal to -4. So those x-intercepts were because of these 2 factors upstairs. So those 2 factors became that. The shared factors became the POD, and then the individual factors became the vertical asymptotes. When you have it in factored form like this, those are really, really quick and fast and nice. So probably one of the biggest things you're going to find is getting it into factored form takes you the most time out of anything. Once you have it there, we got a whole bunch of information very quickly from this form. So I could also get my y-intercept as well. So y-intercept is just when your x is 0. So I plug 0 into each and every one of these x positions. So I'm going to plug a 0 in here, 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 here. So up top you get 2 times -1 times 4, which is -8. And then down bottom I'm going to also get -8. So -8 divided by -8 gives me +1. So it is going to have a y-intercept of +1. Now, one of the things that will happen here that might weird you out a little bit is actually what I have listed on this screen over here. So my slide screen, I guess. Oh, no, I've already talked about that. This is the one that I had gone ahead to earlier. This one, not all asymptotes are the same. So vertical asymptotes are hard asymptotes. They are actual discontinuities, and the graph is not allowed to be equal to that value. So vertical asymptotes are domain problems. So you can't have a graph there. Horizontal asymptotes are nothing like that at all. So vertical asymptotes are kind of funny in comparison to horizontal because we use the same word for both of them because it's a behavior as you approach this line that doesn't really exist. But the way that they behave in different ways is actually not the same at all. So you can never cross through a vertical asymptote. However, a horizontal asymptote is only describing end behavior. It only tells you what happens way out here. So way out here. In the middle, the horizontal asymptote's meaningless. It doesn't tell you that the y value is not allowed to be equal to it. It just says, hey, somewhere way out there, we're at a 3. Somewhere way out there, we're at a 10. What about in the middle? Can you be, or approaching a 3 or approaching a 10? Can you be a 3 or 10 in the middle? You absolutely can. So what's happening that's a little bit odd in the example that I'm doing with you right now is that we have a horizontal asymptote that's 1, and we have a y-intercept that is also a 1. So we are going to have our y-intercept actually crosses through the horizontal asymptote, and that's totally okay. So let's go ahead and just do a quick sketch of this and see what it looks like and how we can, I guess, graph something like this. All right, so let's go ahead and put some of these important points down. So first of all, we have a horizontal asymptote at x is equal to 1. Really good dotted line. All right, so we have a vertical asymptote at x is equal to -1 and x is equal to +4. I don't even know how I made those things squiggle so much. All right, and next up, I have a point of discontinuity at -2. That's hard to plot without knowing exactly where my graph is. So I'm going to wait and see. Now, one of the tricks is you can basically, this is what causes the point of discontinuity. So if it wasn't there, you can know what the y value would be if it was. So if I put everything into the rest of the stuff there, it actually becomes add a value of, where is the point of discontinuity? -2. So it would be -3 times +2 is -6 over -1 times -6 is +6. So I think it's +6 and -6. I can't even remember. That's how good my memory is. So I think it's -1. So maybe. Well, I'm just going to see if that makes sense on the graph. But I think if you plug those values in, that's what we get. So we got our horizontal asymptote. Check. We have our 2 vertical asymptotes. Check. Point of discontinuity, we're going to make sure that we have a hole in our graph at that spot. Great. X value of 1 and an x value of -4 are going to be, x value of -4 are going to be our x-intercepts. Now, I haven't labeled this like I should. Everything, we're going to go 1, 2, and then 1, 2. Everything will follow accordingly, so gaps of 1. And then a y-intercept of 1. It's right here. Now, if I was a betting man, my guess would be that it would look like this. Now, some reasons why I think it looks like this. Out this way, there are no x-intercepts. So if we started below the axis and we approached this horizontal asymptote, you'd have to go through the x-axis. So I think it's safe to be up in this part when we have the graph over here. Likewise, unless this was a bounce, which we did not find a multiplicity there, it was just a single root, it would have to, if it had a multiplicity, it could come up this way. And I know because of the y-intercept that it has to be there right now. So I'll go down and then pass through, and then I'll stay on this side, so I'll come down here. In the other direction, again, because we do not have at this spot right here an x-intercept, I have to go up instead then as I go towards that vertical asymptote, so I'm pretty happy with that shape too. for the last one, since I know it goes through here and it follows along here out towards the end, it would be okay to cross through the horizontal asymptote. But again, this isn't a bounce. It was a single multiplicity. So instead of having it bounce and come up like this, I have to come down here, and I can't come back up somewhere because there's no other x-intercept. So I'm pretty happy with that picture. Now, if you wanted to do a better job on that picture of making sure that you're happy with things, when we found the vertical asymptotes, all I did was say, hey, there is one here, there is one here. If you do one-sided limits and come into each one of them from the left and the right, then you can actually determine whether it shoots up towards positive infinity or shoots down towards negative infinity. So that will help out a lot if you already know which way those are going to go. Then you don't have to kind of play the educated guessing game like I'm doing, where I'm like, well, it can't go through here because it can't bounce. But both of those are fine. So what I'm going to do is I'm going to compare my graph, specifically my purple. I kind of just drew yellow on top of everything there, but the purple is what I want to compare this to. So I want to take this and graph it. I'm going to just pull it up there so I can see it. So in its factored form, it's x plus 2 times x minus 1 times x plus 4 all over x plus 2 times x plus 1 times x minus 4. All right, so let's see how we did. So this is what I have here versus what I drew over here. It's not bad. So first of all, just to make sure that things seem to be okay in terms of the location of asymptotes and things, if I drew in one at -1 and one at 4, then those look good. They kind of frame that part of the function the way they're supposed to. I said that there was a horizontal asymptote at 1, which would be right there. That looks good too. Looks like it's right in between, which it should be. And then we have all of our intercepts, which we can come along and click on. So this one's at -4, 0, which we have down there. We also have 1, 0. That's good too. And we have 0, 1 for the y-intercept. So everything's looking great. If you remember, before I got into making sure I graphed it right with this stuff, the amount of work between this, which is my factored form, and this set of information that comes after it was actually pretty nice. It was a reasonable amount of work, and it was mostly just identifying what each of those pieces did. So again, the ones I have here in blue, x-intercepts. Because this exists as both kind of an x-intercept and a vertical asymptote, is neither. It's a point of discontinuity. So point of discontinuity, things that are in the denominator, the factors there, are vertical asymptotes. So we could list those very quickly. This has to do with the power, the horizontal asymptote has to do with the power of the numerator and the power of the denominator. So we compare those orders together and see whether you're getting the 0, whether you're getting a plus or minus infinity, or whether you're getting the ratio of the coefficients. Once you have that, everything is done except for the y-intercept. You can just plug in an x of 0, see what your y-intercept is, and you'll have this set of information from that discussion every time. I was going to do slant asymptotes, but it's 54 minutes right now, which is a little bit rough. So hopefully maybe you broke this down into bite-sized pieces. Maybe you didn't watch this at all and are handing in your assignments anyway by magic. Whatever the case may be, I hope that you, if you stuck it out this long, I hope some of that was useful, and you can give it a try with some of the textbook questions and let me know how it's going. Take care, folks. didn't yawn for like the last 5 or 10 minutes, so I'll give you a big yawn.